This is Lab 3 on the motion of an object around a black hole. In this lab, I was tasked with estimating the mass of a black hole by finding the net force on the star moving around the black hole. Based upon the trajectory of the star that was unique to my email address, the position data was found that was then used to find the net force. This correlates to Newton's second law of motion, where the rate of change of momentum of an object is directly proportional to the net force acting upon it. The equation dp dt is equal to net force can be broken down to solve for each component of the net force, the parallel and perpendicular net forces. The only force acting in the system is the gravitational force of the black hole on the star, which is an attractive force. The initial conditions for the system were solved for in the computational model, such as the trajectory that gave the position data. The mass of the star is 2 × 10⁻³ kg. The motion of the star around the black hole is circular motion, but the black hole is not in the center of the circle, so that the speed of the star changes and is faster closer to the black hole and slower farther away. This is why the net force, the orange arrow, is longer as it gets closer to the black hole. The perpendicular force, the magenta arrow, always points towards the center of the circle and correlates to the curving of the system. And the parallel net force, the cyan arrow, points along the direction of motion, or opposite to it, depending upon how close the star is to the black hole. To create the computational model of the star moving around the black hole, the position data is first found and then used to find the final initial velocities so that the change in momentum can be found and then divided by the change in time. The rate of change in momentum is equal to the net force. Next, the components of the net force can be found, first being the parallel net force by solving for the unit vector of momentum that indicates the direction the momentum is moving. It is then multiplied by the change in initial momentum. To find the perpendicular net force, the total rate of change of momentum is subtracted from the parallel rate of change of momentum. This is done rather than solving for the perpendicular force separately with the equation mass times velocity squared over r, because this cannot be done as the distance from the center of the curve is not known, nor is the same everywhere as the black hole is not in the center. To find the mass of the black hole, the equation for gravitational force is rearranged. As the gravitational force is the only force acting, it is equal to the net force. The mass of the black hole is proportional to the net force. This means that the mass of the black hole is not constant when calculated, leading it to be higher closer to the star, as high as 8.6 × 10⁻³ kg, and smaller farther away, as low as 8 × 10⁻³ kg. To estimate the mass of the black hole, I found the average of all masses at different positions and estimated it to be 8.29 × 10⁻³ kg. For the error scale, I made it relatively small to allow for the black hole to be seen in the computational model, while still representing the magnitudes of the net force components at different locations. Mathematically, the rate of change of momentum and its parallel and perpendicular components are equivalent to the net force and its corresponding components, according to Newton's second law. The difference between the parts is that one causes the other. If there is a rate of change of momentum, then there is a change in motion that is caused by a non-zero net force. So the net force causes the change in motion. The parallel dp dt is caused by a parallel net force that slows down or speeds up the system, while a perpendicular dp dt is caused by a perpendicular net force that causes the system to curve. The parallel and perpendicular dp dt are added to get the total rate of change in momentum, the same as the parallel and perpendicular net forces are added together to get the total net force. If a different black hole replaced the current one, it would be impossible to tell the difference and find a new mass, because the motion of the star remained the same. Because the position data found remained the same, the velocity, momentum, and rate of change of momentum components remain the same, even with a new black hole. None of the values used to calculate net force change, so when the mass of the black hole is calculated, with the gravitational force rearranged, there would be no difference and the estimated mass would still be 8.29 × 10⁻³ kg, as the mass is proportional to the net force.